Hello everyone, I'm Caleb, and welcome to Wattage Wisdom, where we believe that anyone with the right motivation and internet access can become an expert in any field they desire. In this video, we'll be going over some helpful techniques that will allow you to build a more accurate, artificially intelligent neural network. Also, please remember to like, subscribe, and reach out to us over email with any questions, topic suggestions, or if you want to collaborate with us and start making some videos of your own. So during our model development process in the last video, I provided you with simple steps of constructing your own artificially intelligent model. If you are unfamiliar with how to build your own neural network or have not watched my previous video on the development process, I recommend you go back and give it a watch, as we will be building off of these foundations and cover a wide range of other layers, functions, and overall considerations so that you can construct an accurate model that can generate correct predictions. Before we get started, let's first take a look at what neural network accuracy looks like and how we can spot areas in our model that may need improvement. One of our biggest concerns when training a neural network is trying to create a network that is neither overfit nor underfit, meaning it has learned things from the training data like feature or pattern recognition and is then able to make generalized predictions on new data it has not encountered before. This is where the term overfitting and underfitting comes into play. We will start with underfitting, as it is generally much less of a concern and is easily fixable. Underfitting is when a model is unable to capture any relationship between input and output. This means it is making wild guesses as opposed to thoughtful predictions. A clear sign of underfitting is when your model's training loss and training accuracy are low. If a model is unable to accurately predict data it has been trained on, there is no way it will be able to make predictions about data it has never seen before. So, if you're evaluating your model and you have an extremely low training accuracy, that is a good sign your model may be underfit. Fortunately, there are a few easy remedies for an underfit model, and they are quite intuitive. The first is to increase the model complexity. This means giving the model more dense layers or increasing the size of your dense layers. This gives the model more memory, so it may map out a relation between input and output. Another simple solution is to just increase the training time, which is done by fitting your model with a larger number of epochs. So now we'll move on to overfitting. In general, overfitting is when your model fits exactly or too closely to the training data. This means your network has memorized the specifics between each training input and its associated output. A network that is overfit will no longer be able to generalize and will perform poorly on data it hasn't seen before. To look for signs of overfitting, you will want to view a plot of your model's accuracy while training. Remember that the model.fit method used to train your model returns the history metrics throughout the training process. If you see similar results to those above, you can be assured your model has overfit. As you can see, the training accuracy is continually increasing while the validation or test data is constant and may even be slightly decreasing. This is because during training, your model will continually update itself to generate better predictions on the training data, while the validation or test data acts as new inputs that the model has not seen or been trained on before. There are quite a few remedies you can use to combat overfitting, and the first is exactly the opposite of underfitting, which is to reduce the model's capacity. By reducing the model's capacity, you can force it to map out generalizations about inputs rather than memorize the exact input and its associated output. Unfortunately, there is no one-size-fits-all for model complexity, as this is something that must be fine-tuned to your specific application. And so when developing your model, it is recommended to start with very few learnable parameters, meaning a small number of layers and making the size of those layers small. Then you can generally increase the model memory as needed. Of course, having more training data will always help your model become better at generalizing. However, we are usually restricted by this parameter, and so we will take a look at some of the following methods which can help us combat overfitting, like data augmentation and other regularization methods. As I just mentioned, many times you are limited in the amount of training data that you have, as this is out of your control as a designer. Fortunately, this is where data augmentation comes in to save the day. Data augmentation allows us to generate additional training inputs through various augmentation techniques. It is commonly used where we only have a limited amount of training data. However, using data augmentation can also be beneficial in general practice as it adds a bit of uncertainty and variation into your training data, and this forces your model to map out more generalized features, which greatly reduce the model's chances of overfitting. There are a variety of techniques you can use for data augmentation, and Keras provides helpful layers which make the process easy. These techniques involve adding some sort of alteration to the input so it is different than the original data. As you can see in the picture or example code, some common data augmentation layers can allow you to flip an image, rotate it, change the brightness, or even cut a portion of the image out. You can also search Keras to find many additional layers that will perform other alterations. To apply these data augmentation layers, you simply add them as the first layers in your sequential model. You can also specify a variety of parameters in your augmentation layers, like how much you will allow an image to rotate, zoom, or which way you would like it to flip. By default, these layers are applied at random to your input data during training. It is important to note that these layers are not active when you are evaluating the model or using it to predict classifications. So don't worry about it manipulating your model's accuracy during the actual implementation and testing of your model. Instead, these layers are only active while training so that they can artificially create additional training data to produce a more efficient model. So overall, data augmentation layers are easy to implement and have a wide variety of benefits, meaning they're a smart add to any machine learning model, even if data limitations are not an issue. As we mentioned when talking about overfitting, there are a variety of other regularization methods that you can use to help prevent your model from overfitting. The first one we'll go over is dropout. Dropout, as the name implies, is a process that randomly drops out or sets neurons to zero during the training process. This can be observed in the picture, where a certain number of neurons are randomly dropped out during each training cycle. The specific neurons dropped out are selected at random and change after each update cycle, meaning after each batch is processed. This keeps the network from relying on just a few specific neurons with larger weights and can help create a more normalized distribution of weights, which reduces the chances of overfitting. Dropout is fairly easy to implement with the use of the dropout layer. This layer is placed right after the dense layer, whose output you wish to drop out, and you must pass it the required parameter, which is the dropout rate. The dropout rate is the specified fraction of neurons that will be dropped out and is usually set between 0.2 and 0.5. In the example code, the dropout rate is set at 0.2, meaning that 20% of the layer's output features will be randomly dropped out during training. Also note that dropout does not increase or decrease your model's overall parameters as seen in the model summary. When applying dropout, you may also notice that your training accuracy may appear to remain below your validation accuracy. This is because when neurons are dropped out during training, it can affect your model's ability to make its best predictions. However, don't worry. Just like data augmentation, dropout will only be applied during training and not during testing, evaluating, or implementing the model. Some other popular regularization techniques are weight regularization and weight decay. Not only do these help you build a more accurate model, but they also have the added benefit of reducing the time required for training, which is a topic we'll cover in a future video. So to start, weight regularization is a technique that seeks to encourage the neurons in the model to take on small weights. It does this through changing the loss function so that larger weights result in a larger penalty for the overall loss score. Now, since the goal of a model during training is to minimize the loss function, this added penalty for larger weights penalizes model complexity and forces the weight coefficients to shrink during the optimization process. Overall, these smaller weights help the network generalize better, as larger weights often make the network unstable as it is now more specialized to the specific training data. There are two main types of weight regularization. Those are known as L1 and L2. Both of them operate in a somewhat similar fashion as they apply a new regularization term to the loss function. As we can see from our generalized cost function, our added regularization term includes the weights, labeled here as W subscript J, and a specified parameter lambda. For L1, the regularization term includes the absolute value of the weight's magnitude, while the L2 term includes the weight's squared magnitude. Both of these regularizers are multiplied by lambda, which is a parameter that is manually specified by you as the developer. You must be careful when choosing your value for lambda, as setting it too small will cause it not to work as an effective regularizer, since when lambda equals or approaches 0, you can just see that we get back our original cost function. Or if lambda is set too high, it will penalize even small weights, which will force your weight coefficients near 0 and drastically underfit your network. So it's recommended that when searching for the optimal lambda value, that you initially start with a small lambda around 10 to the negative 3 or 10 to the negative 4th, and then slowly work your way up if you desire more regularization. So moving on, the other popular type of regularization is known as weight decay. Now I want to dispel a common myth. Oftentimes you'll hear that weight decay is the same as L2 regularization. This came to be because for many optimizers that do not use momentum, weight decay and L2 do end up being the same. However, for modern optimizers which utilize momentum, this is not true. The difference is that weight decay is a technique that does not modify the loss function at all. Instead, it modifies the update step. This can be seen in the coded update step, as the new weight decay term is included in the update step, where we're subtracting a little portion of the weight at each step, which is equal to the learning rate times lambda times the weight. Again, lambda is an added parameter that is set by the user and is typically somewhere around the value of 10 to the negative third. So one reason many developers cannot harness the full power of weight decay is because they are choosing optimizers which are falsely applying weight decay. For example, one of the most popular optimizers, which I've even used in my previous examples, Atom, is actually implementing weight decay wrong. This has been outlined in a research paper by Dr. Loshkovic and Dr. Hutter, where they have proven that the Atom optimizer computes weight decay in a way that makes it equivalent with the L2 regularizer. This discovery led to the implementation of Atom W, which correctly implements weight decay by decoupling it from the gradient update. Implementation of Atom W can be seen in the example code and is fairly easy to follow, as it is similar to the original Atom optimizer, where you're going to pass it your desired learning rate and weight decay as arguments. I also want to mention that both the learning rate and weight decay can be either constants or functions. Using functions for these parameters allows you to create either a learning rate or weight decay schedule. Here, I've developed a weight decay schedule which will continually decrease. Generally, you're going to want your weight decay and learning rate to decrease as you progress through training so your model can converge on an optimal set of values. Another helpful trick you can use to train a more accurate model is batch normalization. This technique involves normalizing each layer in the neural network. So traditionally, we wanted to make sure our input data was relatively normalized before sending it to our network. However, with batch normalization, we will now normalize the output of each fully connected layer before sending it to the next layer. This process reduces the internal covariance shift of the neurons in the hidden layers and provides the network with a multitude of benefits. The first is that it allows you to train your model to the same accuracy with less epochs. So since using batch normalization does involve a few more calculations, it will actually increase the training time for each epoch. However, it will also cause your model to converge faster, requiring less epochs, which ultimately conserve overall training time. Another benefit of batch normalization is that it can reduce or eliminate the need to standardize your inputs. So, while we previously needed to make sure all of our inputs were between 0 and 1 before sending it to the model, we can instead just feed it our raw inputs directly to a batch normalization layer before feeding it into the rest of our network. Batch normalization also reduces the chance of overfitting and can decrease the need for other normalization techniques like adding weight regularization parameters or dropout, which is going to increase the simplicity of our model and make it easier to read. In fact, batch normalization actually performs better if you reduce the other regularization techniques inside of your model. To implement batch normalization, all you need to do is apply the batch normalization layer provided by Keras. When using this method, you can choose to apply batch normalization either before or after the activation function. It's generally recommended that you apply batch normalization after the activation function, as it can improve the efficiency of the model. This is done on the second dense layer in the example code, where I first have a dense layer, then I apply batch normalization, and then I apply the activation function. So in review, batch normalization is a powerful layer that can greatly increase the efficiency of our model. Next, we will talk about hypertuning and how to use the built-in functions to tune your model's hyperparameters and generate a more accurate network. As an overview, hyperparameters are constant variables that affect your model during the training process. These can be things like the number of hidden layers or the size of those hidden layers, or they can also be parameters that dictate your training algorithms like the learning rate. Hypertuning is a process that involves searching for the optimal values of these hyperparameters that will result in maximizing a specified metric, like say your model's accuracy. There are a few different ways you can build your hypermodel. You can either construct a model regularly, like we've done previously, or you can subclass the hypermodel class in a Keras tuner. For simplicity, we will stick with what we know and first build our sequential model regularly. Note that when we set the parameters of our sequential model, we are defining the minimum and maximum values as well as the step size. This is done in the example code by setting units equal to hp.int, specify units, minimum value, maximum value, and step size. Also be aware that certain layers should not and cannot be tuned, like our output dense layer with 10 neurons must remain, as it correlates to the 10 classes of images. So once our model is built, we then need to compile it. The only difference here is that our optimizer has a learning rate with multiple values that can be tested, so the ideal learning rate can be found. This is specified by setting the learning rate equal to hp.choice, specify learning rate, followed by possible learning rate values you would like to test. So after our model has been built and compiled, we can now move on to instantiating the tuner. Keras currently has 4 tuners available. There is random search, hyperband, Bayesian optimization, and sklearn. I chose to go with the hyperband tuner as it can provide an order of magnitude speedup compared to the other tuners. This is because it uses a tournament-style bracket between its large number of created models and only carries forward the winners to be further trained. But of course, feel free to research these tuners on your own and go with the one that you believe is ideal. So when instantiating a hyperband tuner, you are required to pass it your hypermodel. However, it's also a good idea to tell it the objective you would like to maximize. Here, I just have my tuner set on maximizing validation accuracy. That's generally what you're going to want to go with. I also specified the max number of epochs to save time. So now we'll use this tuner to run a hyperparameter search, which is done by using the tuner.search function and passing it the same arguments as you would a regular model for training, like your training data, validation data, and optional callbacks. From there, we can find the optimal hyperparameters by using the tuner.get best hyperparameters and use this to manually build our ideal model. Or we can use the tuner.hypermodel.build function to automatically build a new model with our newly found ideal hyperparameters. With this optimized model, we can then train and apply it as usual. One last thing I would like to mention is that there is usually a specific number of epochs that will work best for training your model. This is something you'll want to explore by first training your model for a large amount of epochs, and then through viewing the validation accuracy during the training process, as shown through a normal history graph, you can find the number of epochs that result in a well-trained, accurate model. So this is a basic run-through of how you can use hypertuning to find ideal parameters and build a more accurate model. The last helpful hint I would like to cover in this video is the use of a Lambda layer. This very useful layer is included with Keras and allows you to turn any arbitrary expression or mathematical operation into its own separate layer inside of a sequential model. This can come in handy anytime you want to perform an operation on data that is not supplied or included in any of the existing layers, and allows complete customization of your model, as you now have the freedom to turn any expression you want into a layer and include it in your model. For a trivial example, let's say we have a model with a few dense layers and we wanted to include an operation where we multiply each element by 2 and then add 4 before passing it to the output layer. Note that I'm not sure you would actually want to do this in your model operation. I'm just including it here kind of as an example to show you how you would go through using this Lambda layer. So to create our custom Lambda layer, there are 2 easy steps we need to take. First, we need to define the method with the operation we would like to complete. Here, I'm defining a function that will take an input tensor, multiply each element by 2, add 4, and then return the value. Now that our function has been defined, we can simultaneously turn it into a layer and add it to our model by calling the model.add lambda name of our function, which I've specified as example operation. We can now view a model summary and see that this Lambda layer takes in an input tensor from the second dense layer, completes its desired operation, and outputs an identically sized tensor to the output layer. Also, as we would expect, this customized layer we have created does not have any parameters, as is only designated to complete a mathematical operation. So that's the basics of implementing a Lambda layer. However, I would like to mention that this layer is convenient for simple operations like I've done in our example, but is not recommended for complex computations. Instead, for that, you should plan to use a subclass layer for anything that requires significant computations. Now, this process is a bit more complex, and I'll cover that again in a later video. So that concludes this video on how to build a more accurate neural network model. I hope you're now aware of some common challenges you will face as a designer, like overfitting, and how you can combat those effects. You should also now know a few tricks you can use to further increase the accuracy of your neural network. Please review these techniques as needed, try to implement them on your own, and see if you can produce some of these same accurate results. As always, thanks for tuning in. In the next video, I'll go over the other greatest challenge faced by AI designers, which is how you can reduce the training time of your neural network. So don't forget to like and subscribe so you can continue on your journey with us into the world of machine learning. With questions, topic suggestions, or collaboration ideas, you can always reach out through email at wattage.wisdom@gmail.com. And never forget that with the right motivation and internet access, you can become an expert in any field you desire.